Hello and welcome to this video. In this lesson I would like to discuss the use of the frequency response or Bode plot to aid in designing a compensator or controller in a second order system. Now, let's assume that you know something about second order systems, and we'll do a quick review of how we might describe a second order system before diving into the material specific to this lesson. So I've described a second order system here using its ordinary differential equation description, which is shown right here. Using the ODE description, we can go through the classical process of finding the homogeneous response and then the particular response, and then combining those together and satisfying initial conditions as a way to arrive at the complete response of a second order system. Let's suppose that the input U was a unit step. So by going through this process, we could solve for the unit step response of our second order system. And depending on the value of zeta, we would either have an underdamped or an overdamped or underdamped to varying degrees response. The second response or second description that we use for describing a second order system is its transfer function response. G of s is equal to omega n squared over a second order polynomial, which looks just like the characteristic equation or auxiliary equation that would come from solving the ODE. In this case, we can find the homogeneous or natural response by looking at the poles of the transfer function. And when we solve for the poles, we end up with two poles, two values of s, and we see the convenient form now that we profit from by using the damping ratio and omega m n form of our second order system description. So we have a homogeneous response, which have obviously the same form as what we would find from the ODE. And for solving the particular response, we can use the magnitude and the angle of the transfer function. Specifically here, assigned u of t to be a sinusoidal excitation. So this is just steady state sinusoidal analysis or AC analysis. And the response of the system is sinusoidal with the frequency omega t, but now with a phase shift and a magnitude scaling that is according to the angle and the magnitude of the transfer function when it's evaluated at omega, the frequency of excitation. A third response or description of the system is the impulse response description. So instead of having any kind of a mathematical description in S, we might have a time domain description of the system when it's struck with an impulse at time 0. We might also actually have a unit step response. I didn't draw that here, but the unit step response is simply the integral of the impulse response. So either one of these responses in time would actually contain the same information as the information in the transfer function. Now, for the purposes of doing closed loop system feedback design, if we were given an impulse response description of the system, we would likely take the time domain response h of t, the impulse response, or the unit step response g of t, and we would extract the ODE or a transfer function from the time domain response. So in the end, I'm going to assume that we will either have the ODE or the transfer function at our disposal. So we won't look any further at the impulse response at this point. The fourth of five possible descriptions would be a direct frequency response plot of the system. So although this comes from the transfer function, we may not actually be given the transfer function. We may be given some data, some numerical data that is the magnitude frequency response and the phase frequency response of the system. And here I've shown an example for a particular second order system. You see that the magnitude is 0 dB. For low frequencies. It peaks at a frequency, and then it starts rolling off at a gain or at a rate of -2, meaning 2 decades of magnitude for every 1 decade of frequency, and this is characteristic of a second-order system. The phase begins at 0 degrees, and it arrives asymptotically at -180 degrees, which again is also characteristic of a second-order system. It can contribute at most 180 degrees of phase lag. Now, in this frequency response description, we have a couple salient frequencies and amplitudes that we want to point out. The first is omega r, which is the peak magnitude frequency. This is the frequency at which the magnitude reaches its peak. Mr is actually the value of that resonant peak. And lastly, and most familiar, would be omega n, which is the natural resonant frequency. Now, omega n is the frequency at which this second-order system would naturally oscillate if it had no damping, so if zeta was equal to 0. In this frequency response plot, it happens to be the frequency at which the angle of the transfer function is -90 degrees, right here. And you can check this if you plug in s equal to j omega n into the term s squared plus 2 zeta omega n s plus omega n squared. You'll find that this first term and third term cancel, and we end up with we end up with 2 zeta omega n squared times j, and since this is in the denominator, we actually have a minus j, which is -90 degrees. So these are 3 salient points that are easily identifiable on the Bode response or Bode plot of a second-order system. The peak frequency, omega r, the actual magnitude of the peak, and then thirdly, the natural frequency, omega n. Of these 3, omega r and mr are the easiest to spot, and omega n can sometimes be difficult to spot if there are other terms in the transfer function besides just purely this term right here. Okay, for the moment we'll ignore that, and we'll assume that we are only dealing with this system right here, right? So only 2 poles, complex conjugate poles, no zeros, no finite zeros, and no other poles. In that case, it should be very easy to spot omega n as well, because we simply evaluate the frequency when the phase is -90 degrees. Notice that mr, the peak amplitude, does not coincide with omega n, the natural resonant frequency. In fact, omega r, the frequency where that peak occurs, is always less than omega n. It'll be to the left slightly. Now, we'll see that for highly underdamped systems where zeta is small, then omega r approaches omega n. And so we'll be able to make the assumption that these frequencies are one and the same if zeta is small enough. Now I have here some details on determining what is mr and what is omega r. All right, and you can pause the video or look at the link in the video description to get a PDF of this. But what we're essentially doing is we're looking at the magnitude of the transfer function, this is the closed loop transfer function, and we want to know where the peak is. So that's going to occur where the denominator is minimal, and that's going to occur where the radical of the denominator is minimal, and so we want to take the derivative with respect to omega of the radical in the denominator, and we want to set that equal to 0. And when you do that, we find that omega r is equal to omega n times the square root of 1 minus 2 zeta squared. This looks familiar, but it's not the same as what we have seen before, which is the dampened frequency has a similar definition. It's omega n times 1 minus zeta squared. There's no 2. Recall that omega d is the dampened frequency. This is the frequency at which the system would naturally oscillate if you simply gave it some initial state, some initial energy, and along with a, some non-zero zeta, the system will oscillate as it decays, and the frequency at which it oscillates will be omega d. And so we can conclude that there is this ordering between these three frequencies. The natural frequency, undampened natural frequency, is always greater than the dampened natural frequency, omega d, which is greater than the resonant peak frequency, which is omega r. We also can, from this, calculate then what the peak magnitude is. We plug in omega r to the magnitude expression for g of j omega, and we do some arithmetic, and we arrive at a mr expression of 1 over 2 zeta times the square root of 1 minus zeta squared. Notice that for small zetas, the radical, the square root term, approaches 1, and so we end up with an approximate mr of 1 over 2 zeta for small zetas. Right. And that's convenient because you may recall that there is also another term that's associated with second-order systems, and that is the quality factor. And the quality factor is defined, or related, I should say, is related to zeta as 1 over 2 zeta. So for small zeta systems, we can equate the peak mr with q. So if the peak is 10, we say, well, the quality factor of this system is approximately 10. So we can draw some conclusions at this point. We can say that mr is a strong indicator of zeta. In fact, it is a 1-to-1. There's a relationship there. For small zeta, mr is approximately 1 over 2 zeta, as already stated. As an example, zeta is 0.5, mr is 1.15, which is approximately 1. Okay. Secondly, the attenuation factor alpha, which is equal to zeta times omega n, is obviously related to the settling time, and so the settling time requires both mr, knowledge of mr, which gives us zeta, and omega n. So if we're trying to estimate the settling time, we can estimate zeta from mr, and then we have to find omega n. So omega n may be easily spottable, so to speak, by considering the frequency at which the angle of the transfer function is minus 90, but we can also approximate omega r. We can also approximate omega n using omega r for cases where the damping ratio is small. Now I have plotted here some values. Apologize, my table's not complete here, but actually what I want to focus on is just the ratio here between the omega r, the resonant peak frequency, and the natural frequency, and we see that obviously there's a lot of error for values of zeta that are greater than 0.5, but even at 0.5 there's a 30% error, 0.4, 18% error, 9% error by the time we get to 0.3. So it's reasonable to use omega r in many cases for omega n, and the suggestion would be, say, if I want to have a settling time of 1 second, then maybe I want to design the system using these approximations to meet a settling time of perhaps 2 seconds. The reason I say 2 seconds and not like half a second is recall that omega r is always less than omega n. So if I use omega r, it's a conservative design. In using omega r to estimate the settling time, the actual settling time will be shorter than the settling time that would be predicted by using omega r. So for instance, if the system had a zeta of 0.6, and I used omega r to meet a settling time requirement, in the end the actual settling time requirement would be close to twice as or half as long as what I had designed to. So I certainly will meet the requirement using the approximation. Okay, lastly we want to look at another Bode plot description of our system, and in this case we're looking at the open loop as opposed to the closed loop frequency response of our system. So I've drawn or written out here the open loop transfer function I'm calling G sub OL, and you see that it's in terms of omega n and zeta. If we do GOL of S over 1 plus GOL of S, and we do a little arithmetic on that, you will find that the closed loop transfer function corresponding to this system is S times S plus 2 zeta omega n plus omega n squared, which is the same closed loop transfer function that we've been looking at. So oftentimes, as you know from doing feedback controller or compensator design using the root locus method, is we're given the open loop gain of the system, and we don't actually solve for the closed loop transfer function, but we use the open loop behavior to actually meet some requirements for the closed loop behavior, typically transient or steady state behaviors. So that's the approach we're taking now. Let's assume that the second order system was given to us in an open loop form, and the corresponding open loop transfer function to this second order system that we've been looking at is a type 1 system. Obviously it's second order, and it has poles at 0 and at minus 2 zeta omega n or minus alpha. The Bode plot or magnitude plot of this open loop transfer function is plotted here on the right. And omega 2 is going to be this minus 2 zeta omega n. Okay. And omega 3 is an interesting, is a frequency of interest because it is the point where the magnitude plot is equal to 0 dB, right? 0 dB or 1. This I will call omega t, and it is the unity gain frequency. Unity gain, or sometimes called crossover frequency. And it's readily spotted in an open loop Bode plot because it's where the magnitude is 0 dB or is unity. Now, what we see here also is an extension of this low frequency asymptote here that has a slope of -1 or minus 20 dB per decade. It's extended out here to a frequency called omega 1, and I'll actually come back to that in a little bit as we try to extract some useful information from this plot. But let's just look a little further now at omega t. Okay, omega t is going to be the frequency at which the magnitude of the open loop transfer function is equal to 1. And in the notes here I have derived, or you can go look at the textbook, it derives the value of omega t, but I'll just give the result here. Omega t is equal to omega n times the square root of 1 plus 4 zeta to the 4th minus 2 zeta squared. This is similar to omega r, which is omega n times the square root of 1 minus 2 zeta squared. which is similar to omega d, the dampened natural frequency, which is omega n times the square root of 1 minus zeta squared. So it turns out that omega t lies above omega r, and we know that omega r is less than omega d. Now this doesn't say whether omega t is always going to be greater than or less than omega d, and actually it depends on zeta. So let me show you a plot of that. Here's a plot of the three frequencies. I've also plotted alpha, which is the 2 zeta omega n. This is for the case where omega n is equal to 1. Okay, so omega n is right up here. And we see the orange. This is omega t. It actually, for large enough values of zeta, it does cross over and become greater than omega d, but for most values, meaning the zetas that we typically would consider are going to be when the zeta is smaller, omega t will lie between omega r and omega d. Now, let's think a little bit about this frequency right here, omega 1. Omega 1 is the intersection with the 0 dB axis of the low frequency asymptote of the magnitude curve. In other words, the minus 20 dB per decade curve extended out to higher frequencies, ignoring the presence of this pole at minus 2 zeta omega n. So what we're really plotting in this case here is we're plotting an omega n squared over s times, and here instead of having s plus 2 zeta omega n, we're going to get rid of this s. Right? In fact, when we're at frequencies much less than 2 zeta omega n, right? In other words, down in this region here, the transfer function is, in fact, approximated by this expression here, where the term in the parentheses is approximated as simply 2 zeta omega n. So this is equal to omega n over 2 zeta times 1 over s. Okay. Now this will have a magnitude of 1 when that is equal to 1, which means that s, or the frequency, is going to be equal to omega n over 2 zeta. That's what that frequency will be. Now we can also look at, if you recall, for studying the steady state error of a system, we have the steady state position error. Steady state position error is equal to 1 over 1 plus kp, where kp is the limit as the open loop gain is evaluated with s going to 0. We have the steady state velocity error, which is 1 over kv, where kv is the velocity error constant, equal to the limit as s goes to 0 of s times GOL. Let's consider kv in this case here. We have a limit as s goes to 0 of s times GOL, which is omega n squared over s times s plus 2 zeta omega n. The s's cancel, and we end up with omega n over 2 zeta. And so this omega n over 2 zeta, which is right up here, is actually kV. Okay, this is a significant, useful finding. So what we can do is whenever we have an open loop system with a low frequency slope of -1, that means it's a type 1 system, we simply extend that slope to the 0 dB crossing and pick off that frequency, and that frequency is kV. Now if the zero magnitude was, say, up here, this was 0 dB, then we'd pick off this frequency. We'd pick off that value, and it would turn out actually that would be a value less than 1. So it wouldn't be a particularly good kV, or therefore a very low steady state velocity error, but we could still identify it. Now this frequency here is simply indicating that if omega 1 is equal to kV, and this slope here is a slope of -1, then at an omega equal to 1, we would actually have a magnitude that is equal to kV, or 20 log of kV. Okay, it is not actually used for finding kV. So finding kV is simply a matter of identifying this point here where the -1 slope portion, low frequency portion of the magnitude plot is extended if necessary to cross the 0 dB point, and that intersection is the value of kV, which leads to the steady state velocity error. So the reason I point that out now is that this leads to some other interesting results. Let's bring up a fresh plot here. Okay, so what we have is this point here is 2 zeta omega n. This point here is 1 over 2 zeta times omega n. And so, and if you notice, it's no mistake, these two distances here are equal distances on this log scale. And the reason is that this slope here is a -2 decade per decade slope, whereas this slope here is a -1 decade per decade slope. And so the distance here turns out to be 1 over 2 zeta, and the distance here is also 1 over 2 zeta, and therefore the distance spanned from omega 2 to omega 1 is 1 over 2 zeta squared, right, which is 1 over 4 zeta squared. So this could be useful when we're trying to extract zeta from a magnitude plot. In many cases, it's going to be, it'll turn out to be impractical to get a solid value of zeta by simply looking at the magnitude plot. And so that'll lead to our final topic here, which is going to be related to phase margin. So we'll look at the phase of the open loop transfer function rather than simply the magnitude of the open loop transfer function. But for the moment, let's see if we can extract zeta by simply looking at the magnitude plot. Notice that if you could clearly identify this point here, omega, this pole frequency, right, which is really alpha, and you could identify the zero crossing, omega 3. That is not hard to do. It's going to be whether you can clearly identify the break frequency at omega 2. Then the difference between the two, omega 3 over omega 2, okay, which is, this is omega t over omega 2, is equal to 1 over 2 zeta, because of this span right here. So we could actually find zeta as being equal to 1/2 of omega 2 over omega t. So if omega 2 was 10 and omega t was 20, then we'd have a zeta of 1/2 times 1/2, or 1/4. Okay. The other approach would be that we could extend the -1 slope here. That might sometimes be more useful. Extend this, and if we can identify this frequency and we can identify this frequency, then we can write that omega 1 over omega 3, which is omega 1 over omega t, is also equal to 1 over 2 zeta. All right, so we could extract zeta from this as well. 1/2 of omega, let's see, yeah, that'll be omega t over omega 1. Okay? And lastly, I suppose we could solve it as omega 1 over omega 2, which would be equal to 1 over 4 zeta squared. So we could actually solve for zeta this way as well. All right, which would be 1/2 the square root of omega 2 over omega 1. Oftentimes when looking at an actual problem, it may not be easy to spot omega 2 or omega 1, and so extracting zeta from just the magnitude plot alone could prove difficult. So lastly, we want to look at the phase that's associated with the open loop Bode plot of our second order system. So let us look at the angle of the open loop transfer function GOL, specifically at the unity gain frequency, or the crossover frequency. We evaluate this by recognizing that we have two poles, one at the origin and one at -2 zeta omega n. And so we have two angle contributions. The first angle contribution due to the pole at the origin is -90 degrees. The second contribution is minus arctan of omega t over 2 zeta omega n. We substitute in for the expression for omega t, and we arrive at this expression here. Plotted over here on the right, we see that it begins at -180 for a zeta of 0, and by the time we get to a zeta of 2, we're on our way to -90 degrees. Now, what we're going to look at, instead of specifically the angle of the open loop transfer function, is a parameter known as phase margin. So phase margin first is defined. I'll just give you the definition and we can think about what it means. Phase margin is defined as 180 degrees plus the open loop transfer function angle evaluated at the crossover frequency, at the unity gain frequency. Now recall that our closed loop system is GOL over 1 plus GOL. If GOL equals -1, then we have instability because the denominator is 0, goes to 0. So the -1 of our open loop transfer function is characterized by a magnitude of 1 and by a phase of -180 degrees. Now any odd multiple of plus or minus 180 degrees would also do that, but we're going to focus here on the -180 because that's the first one we're going to encounter as we add more and more phase lag to our system. Now note that by definition omega t is the frequency at which the gain magnitude is 1. So we've already met our magnitude condition for an unstable system. What will determine whether the system is actually unstable is what is the angle at this unity gain or crossover frequency omega t. If the angle is minus 180, then the system will be unstable. And if the angle is close but less than minus 180, then it will be stable but very oscillatory. So the degree to which we are close to incurring the full minus 180 degrees will be an indication of how oscillatory the system is. And so now perhaps this idea of phase margin has some meaning. Phase margin is the distance between the actual angle of the open loop system and the minus 180 degree asymptote line. And we want that phase margin to be positive, and we want it to be reasonably large, as we will see here in a moment. So here's the definition: 180 degrees plus the angle of the open loop transfer function evaluated at omega t. And here it is plotted. The green is the actual plotted expression here, and we can see this is the expression here. And we find that this nonlinear expression function can be approximated as a line for values of zeta that are less than or equal to 0.6, and that's shown right here in orange. So it turns out that if you approximate this as 100 degrees times zeta, you can fit this curve pretty well up to a zeta of 0.6. And that's probably in the region that we'd be most interested in assessing this, because after all, as zeta gets bigger than 0.6, the system is not going to be close to being unstable, and it's not going to be nearly as oscillatory. So the lower values of zeta is where we will want to be using this phase margin expression, and for that we can use this approximate form. If we can determine the phase margin, then we can use this approximation to estimate zeta from the phase margin. Okay, from the phase margin. So now that we know this, we can go back to this one here that we were looking at. Okay, now if I were plotting the phase, we'd be at minus 190, and somewhere before this break point, we'd start losing some phase, and it would bottom out at 180 degrees, minus 180 degrees right here. And if I drew a line straight down here, that's pretty cluttery. Let me just pick off this point here and draw an asymptote here. This distance here, this is our phase margin. Okay, it's the distance from the minus 180 degree line at the point where the magnitude crosses unity. Okay, so we can pick that off pretty readily, and if we can determine the phase margin, then we can estimate zeta. Okay, that's the idea. So now let's just draw some conclusions from this, and we'll wrap up. Some of this is taken, you can see, is taken from the textbook. So okay, the phase margin and damping ratio are directly related. Figure 774, which is right here, shows a plot of the phase margin as a function of the damping ratio, and we have this approximate expression here that is linear. That's useful for values of zeta less than or equal to 0.6. Phase margin of 60 degrees specifically corresponds to a damping ratio of 0.6. That's a useful number to remember. For higher order systems having a dominant pair of closed loop poles, this relationship may be used as a rule of thumb in estimating the relative stability in the transient response. that is the damping ratio from the frequency response. Okay, so this still is useful in higher order systems that have a dominant second order closed loop set of poles. 2, referring to these two equations right here, omega r and omega d, we see that the values of omega r, the resonant peak frequency, and omega d, the natural dampened frequency, are almost the same for small values of zeta. So therefore, for small values of zeta, the value of omega r is indicative of the speed of the transient response of the system. What is this connection? Well, recall that the peak time and the rise time are related to omega d. Okay, the peak time, that's when, in the step response you hit a first peak here. This is T peak. Right? T rise is the point where you first cross unity. Right? So T peak and T rise are both functions of omega d. And so if we can estimate omega d, then we can estimate how quickly the system will respond. And what they're telling us here is that for small values of zeta, omega d can be approximated by using omega r. 3, from the two equations here for omega r, or mr and mp, so the resonant peak is on the Bodhi plot, and mp, which is the transient or the step response peak, we note that the smaller the value of zeta is, the larger the value of mr and mp are. There's a plot here that I've included. It's this figure 775, plotting mr and plotting mp. The correlation between mr and mp as a function of zeta is shown in this figure, and there's a close relationship between the two for zetas of greater than 1. For small values of zeta, mr becomes very large, while mp does not exceed 1. So again, what we're going to spot from the Bodhi plot is mr, and we can use mr and this plot to then estimate what the overshoot is once we know mr. Okay, so if mr was equal to 2.5 right here, I could go down and I could pick off this point here and say, okay, mp looks like it's about 0.5. All right, and then lastly, which is deals with settling time. Now, the settling time is how long it takes for the step response to get within some percentage of the final value. Typically, we use the 2% value, and we know that to be 4 over alpha, the damping or attenuation factor, or 2 over zeta omega n. And here we can estimate the settling time from zeta and omega n. Well, we can calculate it from zeta and omega n, but we can estimate it from estimates of those two. So for small values of zeta, where mr is approximately 1 over zeta, over 2 zeta, rather than 1 over 2 zeta times the radical of 1 minus zeta squared, and where we can use omega r, the peak frequency, in place of omega n, we can express the settling time as 4 times the resonant peak divided by the resonant peak frequency. Now there's going to be error in this, and I have a couple examples here. For zeta of 0.6, we actually have 136% error. For zeta of 0.3, we have 16% error. But in all cases, the settling time will be shorter than what this approximation will indicate. So here's a plot of the exact settling time, which is the orange. So this is exact, and this is the estimate. This is the mr omega r estimate value. And what we see is that the estimate always is going to be greater than the actual settling time. So, if we use the estimate, at least we know that our system will be better than what our approximation tells us. Over here is just a plot of the error as a function of zeta. Okay, so I think I will stop here, And let me see if there's any more. Yeah, there's some other really relevant information that I'd point you to. I pasted in here, and it has to do with more general systems. So we've looked at second order here. I'm assuming you know first order from previous video or lesson in class. But for higher order systems that behave either dominantly as a first or second order system, we can still use these these techniques, these approximations, to arrive at some indication of what we'd expect for a transient response for that higher order system. And the notes here, or the textbook, this 5th edition of Ogata on page 472 and 473, goes through some discussion there, which I think is worthwhile reading. So I think I will stop here, and I believe that you'll have enough information to complete your assignment at this point.